Hello, young scholars. Thank you for joining in on my video review of conservation of momentum and impulse and momentum, the momentum test review. Let's begin with question number 3. In this question, we have an impulse of 14 kilogram meters per second, and we know that it's acting on an object that has a mass of 3 kilograms, and we're trying to figure out the change in velocity. So the first number given is the impulse, which is the F delta t, and this is the mass, and we're trying to figure out what kind of a change in velocity we're likely to see. Well, we know that F delta t equals the change in momentum mv final minus mv initial. And we can rewrite this second term as m times the quantity v final minus v initial. So by just taking the m, by factoring the m out of the equation above, and this term right here, this subtraction, is indeed the change in velocity, since the final velocity minus the initial velocity must represent how much the velocity has changed. So you can see that with that understanding, our equation becomes quite simple. We have 14 equals 3 times the change in velocity. You can take it over from there. Our next question that's a little bit tricky is number 4, which asks you to calculate the change in momentum of a 3 kilogram ball traveling toward a wall at 4 meters per second and then bouncing back at 3. So change in momentum should be the final momentum minus the initial momentum. Change in anything is its final value minus its initial value. And the trick in this problem is not the point 3, that's obvious, that's the mass, but the velocities. 4 and 3 do not work because they're opposite in direction. So we really need to call at least one of those a negative. It doesn't matter which one you call a negative. I'll choose 4 as a negative since it's that way. But the key thing is that the velocities must be of opposite sign. And now we can solve correctly for the momentum, so long as you have the opposite sign of the velocities. So what does that come out to? 7 times, looks like 2.1 is a good answer, but it is a negative 2.1, at least by my chosen coordinate system. Okay. Question 5 is not so bad if you understood question 3, this idea of change in velocity. We can say that F delta t equals mv final minus mv initial. That's our central equation that relates forces to the change in momentum they cause. Our mass can be nicely taken out of that equation above by factoring it out, mv final minus mv initial. The mass is clearly 5. The force is clearly 7. The change in velocity says that this change in velocity here, because it's a final minus initial, must be equal to 2 meters per second. An increase of 2 meters per second. And so the delta t becomes kind of obvious. I'll leave that in your capable hands. Let's move on. Question 6, 6.5, and 7 all deal with the same situation. 2 carts that are initially at rest. Here's a horrible drawing of 2 carts connected by some kind of a spring that is suddenly released. Initially, this guy, whatever has a velocity of 0, that guy has a velocity of 0, presumably. But the one on the left has a big mass, and the one on the right, cart B, has a smaller mass. And the first question asks you, what's the total momentum of the carts after they are released? Well, if we believe in the conservation of momentum, the final momentum after they are released in total must equal the initial momentum after they are released, since momentum has to be the same before and after a collision if it's a closed and isolated system, which this is. So how do you figure out the total momentum after they are released? Simply take a peek at the initial momentum if you believe in the equal sign, and the initial momentum, since both of them have a velocity of 0, must be 0. So the final momentum has to be 0 as well. Question 6.5 is, after the spring is released, which has the greater speed? Well, we don't know. We don't know which one has we don't know the actual value of the speed, but what we do know is that the mass times velocity of A plus the mass times velocity of B must equal 0. A clearly is going to have a negative velocity, something negative, and B is clearly going to be going in the positive direction. But we can see that these guys must be of equal size, or if we move the negative quantity over to the other side, we can write this as mv vb equals ma va. Like I said, we don't know the actual velocities, but we know that if the mass of B is 1 and the mass of A is 3, if this has a small mass, it must have a bigger velocity. And if this has a big mass, it must have a smaller velocity if we want the equal sign to hold true. So even without knowing the actual numbers, we know that the velocity of B must be larger. Question 7.0 asks you to answer the question, after the spring is released, which cart has a greater magnitude of momentum? By magnitude, we mean absolute value. We don't care about the sign. But we know that these two momentums must add up to 0. So for example, if this is 7, this would have to be, wait for it, minus 7. It's the only way you get to 0. And what's the absolute value of those two numbers? You know, it's the same. They must have the same magnitude, although different directions. Boy, I completely gave that one away. Let's move on. Question 8 asks you to evaluate the impulse of some sort of event, and you're trying to make the impulse as big as possible. Remember that the impulse is the force times the time that the force is active. So you want this quantity to be as large as possible. So that means you want the area under the force time curve to be as large as possible. Well, if you have a force that's this big, but with a large amount of time, that seems to help the total area under the curve. That seems to make your impulse bigger. So clearly making your time bigger is a smart maneuver. But also, another way to make your impulse bigger is to make your force bigger as well. So that would even have a bigger impulse. Compare, look at that area versus this area. Huge difference. So we want to have both of those quantities be large. Both the F and the T need to be big. Think of it as a multiplication problem. What's the best way to make this number big? Well, 9 times 9 is a lot bigger than 1 times 9 or 9 times 1. Both should be big. Uh-oh, I've given another one away. I'm sorry. I'll try to do better on question number 10, which asks you, when a bug hits a windshield, the change in momentum of the bug is greater than, less than, or equal to the change in momentum of the car. Well, let's think about this. When they collide, the bug will experience a force, of course, and the car must experience a force as well. Small force, small one, but nonetheless a force. And those forces must be equal because those are our action-reaction pair of Newton's third law. So the forces have to be the same. NL3 must be true. And the other thing we need to consider if we're talking about change in momentum is remember that the change in momentum, mv final minus mv initial, whether we're talking about the bug or the car, it has to equal the force that they feel times the amount of time that they feel that force. Well, we've already clearly stated from Newton's third law principles that the forces must be the exact same. Check. I'm going to let you think about whether the delta t's would be the same or different as you evaluate this, the change in momentum of both bug or car. Next question. Number 13. This is clearly a conservation of momentum problem. For initially we have some momentum of the system, which is composed of the car and the hay. And finally we have some momentum of the car and the hay combined. Initially we have two separate objects, mass of car times velocity of car plus mass of hay times velocity of hay. Well, what is the velocity of the hay? Presumably v equals 0. So that means that this one doesn't contribute at all to the momentum of the system prior to them meeting up. But afterwards, the car and the hay are combined, and it's like the two masses are one. We've got mass of the car plus mass of the hay combined, and they will share one common velocity, a velocity that they both share. And in this equation, let's see what we know and what we don't know. We know the mass of the car, the velocity of the car. We know that's a 0. We know the mass of the car, the mass of the hay, and we want that. Enough said. Okay, I don't have too much to say about question 15 except for we need to be clear that of the initial conditions. And so the initial conditions are we have a boy. He's holding an 8-kilogram medicine ball, and presumably he has a velocity of 0. Although I guess the problem doesn't say that specifically. So that means the initial momentum must equal 0. But as we have certainly learned by now, the initial momentum must equal the final momentum. So make sure you understand the final momentum as the boy on his skates probably rolling in one direction, and in the other direction the medicine ball must be going. And we know that now instead of having just a single term for momentum, we'll have two terms for momentum. One for the mass of the boy times his velocity, and one for the mass of the medicine ball times its velocity. Good luck. The next series of questions asks you to look at the situation that I've illustrated here. And the first question asks you about the average force on the bullet by virtue of the fact that the gun just shot it off. So here we're not looking at a combination of things. We're looking at just the bullet and the force he felt. So this is not a conservation of momentum problem, not yet. because we're simply looking at the change in momentum of the bullet because of the force he felt, a single object. Usually if it's a single object, it's a impulse momentum equation. If there are multiple objects, usually we're looking at the change in momentum of the system staying as zero. Initial momentum equal final. So let's take a look here. We're trying to find the force. That's our object of desire, the force. That's what we want. The delta t, the time of the explosive charge, was given, so that's a check. The mass of the bullet, that's given, that's a check. The final velocity of the bullet, 800 meters per second, that's a check. And same mass of the bullet here. And the initial velocity of the bullet, I think it's safe to say that's a zero. So we know everything in the equation except for the average force acting on the bullet for that very short amount of time. In question 17, now we have a two-object system. We've got a bullet and a block. The bullet has a certain momentum, which is that number right there. And the block has zero momentum because it's got zero velocity. So our initial momentum of, let's do this in green, our initial momentum of this system is all contained in the bullet, no momentum of the block. So as we describe the initial momentum, we would say this is the mass of the bullet, lowercase b, velocity of the bullet, plus mass of the block, velocity of block, uppercase b, but that whole thing is zero. And we know the initial momentum must equal the final momentum, since there are no external forces to our green system. No net external forces. So finally, when the bullet penetrates the block and sticks in, then we've got simply one object. How much mass does it have? Well, it has the mass of the bullet plus the mass of the block. How much velocity do they both share? That's your problem to figure out. Next question. Question 18 asks you to test your faith in our fundamental equation that relates forces and times to change in momentum. And the question is, if you push a bicycle or a car, each will experience the same increase in momentum as long as you push with the same force. So F is the same for the same amount of time. So if these two numbers are the same, whether you're pushing car or bicycle, will you experience the same quantity on the left side of the equation as you do on the right side of the equation? Let's move on. Question 20, skipping number 19, I know, gives you a 3 kilogram mass which is at rest, and it receives an impulse of 20 seconds. When we say that it receives an impulse of 20 Newton seconds, that means this whole quantity is 20 Newton seconds. It says it's initially at rest, so the initial velocity is 0. That's the initial velocity. And your job is to figure out the new speed. That would be the final speed, v. And then your second job in part B is to figure out the new momentum. Well, the old momentum was 0. The new momentum would be this, the final momentum. So that takes care of 20A and B. Skipping ahead to question 24, here's a picture that might help you. You should imagine a 12 kilogram object colliding with another 12 kilogram object, but it has no velocity. They hit, they bounce off. Now object A has no velocity, therefore no momentum. So, and B travels on, and your job is to figure out what is the speed of B. If you're still a little perplexed, remember that the total initial momentum must equal the total final momentum. That'll help you get there. On our last question in the review, we've got a collision between a truck and a car, and they do not all go in a straight line. They're at different angles to each other, and so you should recognize immediately that that means you're going to be having to add these like vectors. That means you will have to calculate a momentum of the truck, get a number. Calculate a momentum of the car, get a number. Can you add these like regular numbers to get the new total momentum? No. You must add them like vectors, which means you have to have an arrow in the direction that the truck is moving that is that big. And then you have an arrow that is in the direction the car is moving that is that big. Draw it to scale. Add those two vectors. Remember, vector addition is tip to tail. You're looking for that. And the total momentum, therefore, will be in the direction of the addition, the summation, the vector sum of those two vectors. I know that's not the actual direction of the truck and the car, but that's the concept. Once you have that total momentum shown in red, you are prepared to find the angle, because the angle can be calculated by either measuring with a protractor. That's one way. Remember that typically we have 0, 90, 180, and 270. So you could look at your red vector and just measure it off. Remember, this is just an example up here. That's not the way it really is. Or, if you're more mathematically inclined, you can always do the inverse tan of the the y part of the momentum divided by the x part of the momentum. And then you have to do a little think about it and make sure you're in the right quadrant. If you're absolutely opposite of the quadrant of the red vector, then you just have to flip it around 180 degrees. This is a super accurate way to get the angle. This is an okay way to get the angle. Both of them will do you just fine on the test. Good luck, everybody. And if you are wanting just a little bit of extra credit on top of doing a complete review, then you can write these words down on your test review, and I know you will have seen it through to the end. Underneath your name, on the front page of the test review, right underneath your name, if you write, I love unicorns, and then make a heart and an exclamation point, I will suspect that you watched this video. Don't tell anybody else, otherwise it has no value to you. Good luck, everybody, tomorrow. We're on the same team. I'm rooting for you. Bye-bye.